Today we are going to discuss proof composition of injective function. So let G and F be an injective function where G maps elements from set A to some set B, and F maps elements from set B to some set C. So these are both injective functions or one-to-one functions, meaning they map distinct elements to distinct elements. Then their composition of f of g is injective, and we'll be proving that in today's lesson. So f of g. Now, since the codomain of g is p and the codomain of f is p, we of course can compose this function. We can consider the composition function f of g quickly before we jump into the proof. What proof? And what are the domain and the codomain of this function. So well, remember, in function composition, the order is from right from right to left. So an element will be evaluated in function g first, and then it will be evaluated in function f. So the element that go through this function will need to start in the domain of g, which of course is the A, set A, set A, then G will be sent to them to some element in the set B, set B, and then of course they can go into the function f, which will take them from B, from B, from B, and then sent to some element in the set C. So it's going to be their final landing place. So this composition function f of g will take elements from A and send them to the set C. We want to prove that given G and F are injective, the composition F of G is also injective, meaning if we take two distinct elements, we'll say, um, meaning if we take two distinct elements, we'll say X and Y from the domain. So these are the distinct elements of this element X is not equal to X. So element of, this is element of A. So we didn't say that X is not equal to Y. Then there are image under this function that are also distinct. That's what it means for this function to be injective. So that means if f of g of x is not equal to uh, what what it means for these functions to be injective. So that means f of g of x is not equal to f of g of y. If we put distinct elements in the function, there are images that come out will also be distinct. Proving this is very straightforward. We basically just have to apply the definition of injective a few times, so I definitely recommend giving it a try to yourself before watching the rest of the lesson. So now let's get into the proof, and we can basically begin our proof with these two lines considering composition composition function of uh, composition function of f of g that maps element from A to C. So we can basically begin our proof with these two lines, considering the composition of f of g maps element from f of g maps an element from A to C. Yeah. Then considering these two distinct elements x and y is not equal to y, and like we just went over, we want to show that the image of x and y is x and y under the function of f of g must be distinct as well as x and y are distinct. And we really just have to think through the progress of this function. So an element is going to start be evaluated into the function to the function of g. And what do we know about g of x? G of x and, and g of y. Well, we know since x is not equal to y, and g of x cannot be uh, g of x cannot be equal to, I mean, it's not equal, and g of x cannot be equal to g of y, because g we're already assuming is an injective function. So if we put these two distinct elements, their images under g will also be distinct of x is not equal to g of y. Because g is injective, then of course since g maps element to p, since g a maps elements to p, we know that g of x and g of y, they are distinct. G of x and g of y are they are distinct elements of this set B. That's the codomain of G. So G sends x and y to distinct element P, and of course P is the domain of F. So there are distinct elements of uh, G of x is not equal to G of y, and they are both elements of B. Then we can consider what happens when we really put two two elements into the f function f. And what do we know about uh, f of g of x, and how it really relates to f of g of y? Well, since f is an injective function, this f here, we know that these two things must not be equal to g of x. uh, it's not equal to g of y, and we assume that f is an injective function. We know that im image of g of x and image of g of y, image of g of x and g of y under the function of f, the function of f, under the function of, I mean, uh, under the function of f, those image must be distinct of f of g of x. F of g of x is not equal to f of g of y. F of g of y, because f is injective, so we put those distinct elements into f, they're gonna come out of. So being distinct, and now what does this look like, my class of the f f f of g of x, f of g of y. By definition, f of g of x, I mean f of g of x and f of g of y. By definition, that's just our function composition of f of G evaluated at X and evaluated at X evaluated at X and evaluated at Y. So this is the same as saying f of G that f of G that composite function evaluated at X not equal to Y. To that composite function f of G evaluated at Y, and this is the line we really wanted to get because this demonstrates that our composition function f of G is injective if we take any two distinct elements from the domain. The ranges under the composition function f of G will also be distinct, which followed easily from the fact that G and F are both injective. G, G and F are both um, are both in, uh, are both injective functions, and so that is our conclusion. Thus, the composite function of G f of G is injective if distinct elements go in, then distinct elements come out. So, and of course, remember that f of g of x, f of g of x, and f of g of y are both elements of uh, codomain, the codomain of C, the codomain of the composite function, since f is the last part of this composite function, and of course f sends element to C, sends, sends element to C. So we just proven that function composition preserve injectivity if we get this pair of injective function. And we compose them, then that resulting composite function will also be injective, and that shouldn't seem too surprisingly, especially if you were to represent this with a diagram. I think it would seem really obvious. So what makes for an easy proof, and it suggests a couple interesting questions. The first one that comes to mind is the converse of this statement true, as well as if we want we know that f of g is injective, does it allow f and g are both injective? And the other question would be the same result, true for some surjective functions. So if we knew that g and f were surjective instead of injective, would it follow that the composition is surjective? I hope you guys learn about proof composition of injectivity.